Mentally present or just physically present? You know? I know I'm physically here, but we'll see how mentally I am. We'll see how it goes. Time to go mental, but not meta, hopefully. Alright. So, hopefully we'll get through most, if not all, of Chapter 5 today. I'm trying to stay a little ahead of schedule, just in case it takes us a little longer to get through something later. So we'll see how it goes. But yesterday, it seems like last week already, but yesterday we left off on the gas laws, so we're going to finish those. We did Boyle's law. We're going to finish Charles' law. We're going to do Avogadro's law, and then we're going to do the combined gas laws. We'll talk about gas mixtures. That might be a little new for you. Does anyone remember Dalton's law of partial pressures? Maybe, maybe not. If not, it'll be a little new. And then this is definitely going to be new for you. Real gases. Okay, this is when it gets real, yo. Okay, so it's always better to be real than ideal, because ideal is just not real. All right. So, so we left off on this last time. So Charles' law. Okay, what does Charles' law say? Well, actually, let's talk about Boyle's law for a moment. Boyle's law says volume increases, pressure decreases, and then vice versa. Pressure increases, volume has to decrease. When you compress a gas, okay, that's decreasing the volume of that gas, but the pressure inside that volume is going to increase, right? So that's Boyle's law. Charles' law is a temperature dependence on the volume, by the volume. So as volume increases, the temperature will increase if all other things are constant. Conversely, if the temperature of a gas is increased, the volume has to increase as well. Gases expand when they get heated, right? So that's a little more intuitively natural to our thinking. So here's a problem, okay, and most of you will probably get this, but we'll see, okay. A gas has a volume of 2.89 liters at 85 degrees Celsius. What then will be the new temperature in Kelvin, okay, if the volume is increasing to 5.68 liters. Okay, and so we're going to plug it into this equation, right, Charles' law. So, how many of you have done a problem using this equation before? Okay, so which one is my V1?
The 2.8.
That one. Which one is my T1? 85, right? Which one is my V2? This one, and it's asking for T2. Okay, try to solve this. Tell me what you get. Okay. And yes, I'm asking you to bring your calculator to class. Does anybody have a result yet? 704
Kelvin.
Or Kelvin. Oh man, you got it right. No.
Should be proud.
I know I should be proud, right? I'm like, oh, I wanted you to get it wrong. Did anyone else get a different answer than that? Just curious. No? Ah, you guys are too good. All right. So, so you know the trick then. What is the trick?
You convert Celsius.
You always have to convert temperature into Kelvin first before you actually plug it into the equation, right? But just to, excuse me, so T2 is going to be equal to V2 times T1 over V1. If you're shaky in the algebra, let me know. But and then of course plug in the numbers, 5.68 liters, and then let's see, in Kelvin, let's see, 85 degrees Celsius plus 273 Kelvin, or 0.15 Kelvin. Okay, so that would be 358. Although in my numbers here, I just put it at 358. Anyway, so 358, and then divided by the initial volume of 5.68. No, wait. Check that. 2.89. See. So yeah, this would come out to be 704 Kelvin. So, question, how come you have to convert it to Kelvin first before plugging it into a gas law? Like, why do we have to do that? Well, what if the temperature that was given to us was 0 degrees Celsius? And plugged in 0 degrees Celsius into this equation. Is that mathematically allowed? It's not, right? You can't divide by 0. That's an undefined result for math. And so just mathematically speaking, you can't plug in 0 into the gas law for that reason. Okay, so, all right, the other thing, oh yeah,
Since it's 85 degrees Celsius, why would the answer be 2 sig figs?
let's see. Oh, okay, yeah. Good question. All right, let's look at the sig figs. So the rule for addition, okay, is you look at the decimal places, right? So 85 plus 273.15, okay, adding it up this way, I get three sig figs from that because we're going by the decimal places, right? So no numbers to the right of the decimal. It doesn't matter with this 273 that's considered to be exact. So just by going by the rule for addition, we keep all the digits to the left of the decimal for that reason. So that the reason why it's 3 sig figs in the answer is because now we have 3 sig figs here from the addition rule. So that's what happened. Thanks for asking. That's a good question. That always is hard to track. Anything else? Yes, I always remember when it comes to the temperature conversion equations, 273 or 273.15, those are exact numbers. The Fahrenheit to Celsius, that 1.8 times the degrees Celsius plus 32, those numbers in that equation are all exact, right? So had we plugged in, had we plugged in the 85 degrees Celsius in here instead of 358 Kelvin, and then gotten the degrees Celsius out of here and then converted it to Kelvin after, you would have gotten 440 Kelvin. Right, so you can see how it really would have thrown off the answer if you did not convert to Kelvin first. Okay. So any questions about Charles' law? Okay, really basic gas laws. You've seen it before. You know them. You love them. Well, maybe you not love them, but you know them. So that's Boyle's law, Charles' law, and then what if we combine Boyle's law and Charles' law? What do you get? You get Charles-Boyle law. Okay. Which is combining the Charles and Boyle's law. All right, so, and then if you combine Avogadro's law, which we'll talk about a little later, you get Charbo-Avocados. Okay. So, and some of you may not even have breakfast in here. I'm talking about food, and you're like, God, Fernandez, come on, go easy on this about the food. So if you know that pressure and volume are inversely related to each other with Boyle's law. And you know that temperature and volume are directly related to each other through Charles' law. Proportionality constant comes from that, and then of course you can solve for that K constant, and you get Vp over T, and then having a before and after with a constant, staying constant before and after a change. What kind of change in gas are we talking about here? Are we talking about physical change or chemical change? This is going back to like the beginning of your chemistry days. Like if you compress a gas, is that a physical or a chemical change? That's a physical change, right? The molecules aren't changing, they're not reacting into something else. So all of these gas laws that we talk about, they're all in regards to physical changes. Compressing a gas, heating a gas, adding more moles to an already existing gas sample, you know, those are all just physical changes. Heck, actually adding more moles of the same gas isn't even a physical change, it's just adding more quantity. So, but it will increase the pressure, so these are all physical changes. We'll get to what you do about chemical changes later. Here's an example. A sample of gas has a volume of 1.23 liters and a pressure of 755 torr at 0 degrees Celsius. What is the volume if the pressure changes to 735 torr and 50 degrees Celsius? So this is just a matter of plugging and chugging, but it helps to take an inventory of your numbers here. Okay, so what is our P1? And so P1, 755 torr. V1 is
1.23 liters.
1.23 liters, right? And then our T1 is
273.15.
0 degrees Celsius. Actually, 0.0, excuse me. 0.0 degrees Celsius. But we know that in Kelvin, this changes to 273. Now, is it 273.15? Is it 273.0? Is it 273.2?
0.15.
So rule for addition, now it's 1 decimal place, right?
So it's 0.2?
So it's actually 0.2 from that.
So you don't just mark the significant figure and then wait to round till the end?
We're not going right. So we're going to go ahead and use. Okay, go ahead and use 273.15. Go ahead and use that, but understand that
that's the last.
That's the last sig
okay.
fig. But we're gonna use 273.15 in our calculation, but we're gonna round it as if it were 273.2. Okay. Okay, and then our P2 is what?
735.
That's yeah, 735. And then our T2
323.
and so it's 50 plus 273, so it's going to be 323. Again, 0.15, but keeping 1's decimal place in mind. And it's asking us for V2. Right? What is the volume?
Are unknown.
Right, our unknown is our volume. So it's asking us for V2. So how do we solve this equation for V2? Doing the math, why not? It's always a good time to do math. So if we have V1, P1 over T1. V2, P2 over T2, how do we solve for V2? So what do we do? Multiply both sides by T2 over P2. Right, and then on this side it would be T2 over P2. So ultimately we have V2 over T2, V1, P1. I feel like I'm speaking code to you, but over P2 times T2, or T1, excuse me, sorry.
I have a question.
Mhm.
So for char-boiled law, you have to rearrange for your unknown. You can't solve the way that you did before.
I'm not quite sure what you mean.
Just because the way that I solved Charles' law was I just cross-multiplied.
Oh, yeah. That was because
Would you be able
of
to do it
the
that
way
way?
that, so let's see, on the last one, I guess we had, yeah, you just cross multiplied on that. But because this one has more variables,
You have to rearrange.
you kind of have to just rearrange it. Cross multiplying works sometimes, but I don't know. I've never gotten in the habit of doing just cross multiplication because it might not work well for everything.
Okay.
I guess in a way we are kind of sort of cross multiplying, but we're, I don't know.
Well, how about we see if we get the right answer? I'll do it the same.
Yeah, do it the same way, see, let me know how it goes. So let's plug in the variables, we'll go over here. Alright, so V2 so our V1 is 1.23 and we have, actually I should put our T1 first. Alright, excuse me, T2. Alright, so T2 is 323.15 Kelvin. And then our V1 is 1.23 liters. And then our P1 is 755 torr. All over. And then 735 times our T1 of 273.15 Kelvin. All right, so the Kelvins cancel, the torrs cancel. So do I have to have torr, and do I have to convert those into atmospheres? And the answer is no, I don't. The only thing you have to worry about is the Kelvin, right? That always has to be Kelvin. But everything else can stay in the units that you want, and if you have to convert after the fact, that's fine. Okay, and the answer would be, and how many sig figs should the answer have? 3. Yeah, 3. So it turns out the temperature numbers didn't play a role in the sig figs. Okay, not directly. Okay, so that would be 1.49.
I did get the same answer.
I got the same one too, and did like she did.
Okay, well then I guess you can cross multiply. I just never think about doing that, but. Okay, so I guess, yeah, cross multiply to your heart's content then. Alright. So when you cross multiply, I guess you're saying, well, I don't know, I guess this goes up here and that goes up here.
Well, I just set everything up like how it is in the very last part, set it up all the same, divide it all on one side, and then I multiply it by the T2 on the left side, and that clears it, and then I just divide it by P1 or P2
Yeah,
on the left side. Like how you would just do normal like math 40 stuff.
okay. I've forgotten my math 40. It's been 20 years, something like that. I probably do things a little more stepwise, but all right. Well, I'm glad it works. Any questions about this? Yes. All right. So that's Charboil law. What if we include standard conditions to this? So does anyone remember what STP stands for?
Standard.
Standard temperature and pressure. And what are those values?
0 degrees Celsius, 22.4.
Well, that's the standard molar volume, right? So 0 degrees Celsius for the temperature, and then 1 atmosphere. So the easiest thing to forget is probably the temperature. So if you can't remember what the temperature is for standard temperature, you just stop yourself and use that big O for the 0. Okay? Alright, so stop yourself before you forget. 0 degrees Celsius is always standard temperature. Of course, I thought it meant Stone Temple Pilots in the 1990s, but what am I? So standard conditions for gases. The volume of the gas is dependent upon pressure and temp, as we've seen. And chemists have agreed to a set of conditions to compare measurements, and those would be STP. And as we just stated, 0 degrees Celsius for the temp, 1 atmosphere for the pressure. Okay, here's a sample problem using that. So now we can have a char-boiled problem, but now it won't give you 5 numbers, it might just give you 3, and then it might just mention STP in there. You know, and when you see STP, that should automatically ring a bell of 2 numbers to you. 0 degrees Celsius, 1 atmosphere. All right, so incorporating STP now. So what is the new temperature if we have these inputted values? So STP, what is our T1? So T1 in Kelvin would be 273.15 Kelvin. That's standard temperature. All right, P1 is, all right, 1 atmospheres. And that's considered the exact. Okay, that's just standard pressure. Okay, and then you have, let's see, our V1. So what is our V1? 2.50 liters. Okay, what is our T2? That's what it's asking for, right? And our P2? Yeah, that is 0.25 atmospheres. And then our V2 is 5.00. All right, now it's just like the same kind of deal. Let's do the math, or cross multiply, which is math. Okay, okay, so we have B1, P1 over T1 equals B2, P2 over T2, and we have to solve for T2. So I guess if you cross multiply T1 over, is that how it goes?
What?
I'm going to reteach myself math 40.
First you would multiply V1 and P1.
Yeah, just do
Oh,
the whole
I see.
left side.
Okay,
first.
so cross multiplying this over to here.
Yes.
Okay, so I'm going to teach myself math on camera. Okay, so we're going to do V2, P2 over T2, and then it's gonna be actually times V1, P1 down here as well. Okay, and then you're also gonna take the T1 over and, okay, so that one goes this way. All right. Okay, but now we have like nothing on this side.
So, make it equal to each other, like.
Do you make them equal?
Oh yeah, this has to come up here, huh?
So that should be
So-
equal to the other.
So it would be T2 equals B2, P2, T1 over V1 over P1. All right,
That's
did
correct.
I do that right?
The equation is correct.
Yeah, all right.
It's
Yeah,
okay,
okay.
just do it your way.
No, it's what I have here too. All right, it's what I have here too. I just never think about it as cross multiplying. I just think of it as, okay, I'm gonna multiply this over here and this over there. I guess that's what I'm doing. I'm doing the same thing, but I just don't think of it as cross multiplying. Okay. So I'm reteaching myself. All right, so you always have to reteach yourself. And it's then have your hand raised? Yeah, Bob.
Can you also do V1 P1 times T2 equals V2 P2 times T1? And then it's software?
Probably. What you said sounds okay. The way I think about it is, okay, I'm gonna multiply this up here and then multiply by the reciprocal on this side. That's how I kind of think about it. You know, but it's the same thing. You know, if you're getting here, you're doing something right. Mental gymnastics on a Saturday morning, gotta love it. Okay, so plugging and checking the numbers in here now. Okay, this should be pretty easy at this point. So now it's T2 times V2, P2, T1 over V1, P1. Okay, so now we have 5.00 liters. We have 0.25 atmospheres. Standard temp divided by, what's this, 2.50? And then standard temperature. Since this is an exact number, we're not going to use it for sig figs, all right? It's just, you know, standard pressure is exactly 1 atmosphere. Okay. So the answer comes out to be, I got 140 Kelvin. 2 sig figs because 0.25 has 2 sig figs in it. Questions? We good? All right. Now, I say hamburger is much more tasty with avocados. Actually, my wife and my kids are going to an avocado festival today, so it's perfect timing. Behind a question.
Quick question. I always know that you don't count like the 1 ATM as
For the sig figs.
But why don't you? Like why don't?
Why?
Like why isn't that just 1 sig?
Because it's considered exact. So when it's exact, it's not measured. It's just relative to this set defined exact number. So like 12 inches are exactly into 1 foot. High is always a certain number, right? So it's like that. Yeah. All right. So adding our avocados to our charbroiled situation, we have Avogadro's law. And this is very similar to Charles' law, same sort of equation, but you got moles into the temperature. It's a direct relationship. If you add more moles of gas to a sample, the volume is going to expand. It's just more gas, right? Proportionality constant, solving for that, you get V over N. Very analogous to how you got V over T for Charles' law. So if you double the moles of gas, you double the pressure and so forth. And then you get that equation. So we could plug in numbers and do a sample problem. I don't think it's really necessary. Now, if you combine Charles' Boyle's and Avogadro's law together